Anyway, let's start with parameterized surfaces and doing integrals on parameterized surfaces. So the parameterization then is smooth. This is a definition of the word smooth in a calculus class. Means that the partials with the two parameters that you're using. If you were here yesterday, we talked about getting Maple to draw parameterized surfaces. These surfaces are traced out by the tip of a vector which will have two variables that we call parameters, and they could be, for example, x and y, and then you'd have to write z in terms of x and y, or they, if you were working on the surface of a sphere with a radius that's constant, then they could be the two angles, the colatitude as it's called, and then the longitude angle. Or if you were on a cylindrical surface, the parameters could be the angle theta and z, or they could be the r. Well, if you were doing a cylindrical volume, it could be the r and then the theta, something like that. So smooth means that the partials with the two variables that you're using as your parameters will be continuous with the cross product of the partial derivatives, never zero over the interior of the domain of the two variables that you're using as your parameters. So this projection factor or coordinate ratio, which is the magnitude of this cross product of partial derivatives, then is essential to computing surface area, as we were doing yesterday. The area then on the surface would be the integral of over the domain of the magnitude of this cross product integrated over the domain. So this coordinate ratio or projection factor is also called the Jacobian. There was a mathematician whose last name was Jacobi, and he was European trained, but he actually came to America and taught at Johns Hopkins, which is a university in Baltimore, I believe. It's in Maryland, I know, and is, well, it's not actually literally an Ivy League school, but it's that quality school in that age. It's a very high-class school, certainly. So he was one of the first high-priced, high-powered European mathematicians to come to America in the, well, I'm not sure, 1840s, 50s, I think, along in there. Anyway, what this Jacobian amounts to is it accounts for the change in scale when you go from one set of coordinates to another. Remember our definition of flux. The reason I'm reminding you about it is that what we're going to be working with are things we call flux integrals. So flux has units of mass transfer, like grams per second per square centimeter across the surface. And I'm using the capital letter sigma for the name of my surface. So a flux integral then would be an integral over this surface. The dot product of the field with the outward pointing unit normal. So it's the normal component then of this field integrated across the surface. So flux integrals then require an oriented surface, which means that you can always say what is your outward pointing normal. Not all surfaces can be oriented actually, but the ones that you can do math problems with have to be orientable in that sense. So what we require then is that if we take the cross product of the partials of our parameterization vector, remember this R is a vector typically in Cartesian form, so it's three components, and as we talked about yesterday, even though the variables may not be x, y, and z in terms of x and y, even if you're using the cylindrical coordinate variables or the spherical coordinate variables, you're still, as a rule, writing x in terms of those. So anyway, whatever the parameters are, you take this cross product of the partials, and that's supposed to define an outward normal in a way that would be consistent wherever you are on the surface. So this is not always the case, but it will be the case for us. So if your surface is if you can define your surface as a function of x and y, then your outward pointing normal, which we first had in chapter 14, would be like this, the gradient of z minus f of xy, and then this would be the magnitude of that. And so this over its magnitude gives you the outward pointing unit normal. So if you have a field with three components, then your flux integral, which is the integral over this orientable surface of f dot n ds, where you're using this for your n, you see you'll have m np dot this thing, and then you have the magnitude of your gradient. I left off a vertical line there. I'm dividing by the magnitude to get a unit normal, and then I multiply by the magnitude of the gradient, which, and again, I left off I multiply by that as this projection factor that I've been talking about, that we talked about yesterday and have been trying to review. So that actually cancels out if it's a flux integral, and it leaves you the dot product of the field if you have it in as a three-component vector, and if you're thinking of the kind of surface that you can define this way. So then if you dot this out, you have minus f sub x m, you have minus f sub y n, and you have p. So you can write a flux integral like this, provided you meet all these assumptions that you have a field, first of all, with components m, n, and p, and secondly, if your surface is the kind where you could write it z as a function of x and y, where like the top half of the sphere, say, like in chapter 14, and then you're using the magnitude of the gradient of z minus fxy as your scale, as your Jacobian or your scale change, which you get out of this cross product. And then it turns out that you have it in the denominator position to make this be a unit normal, and you have it again as your Jacobian or scale factor, and they cancel and it leaves you this. So the more general case is that your surface may not be parameterized with x and y, for example, or that you might be projecting not into the xy plane. In other words, you're not using x and y as your parameters, but you might be using y and z so that you're projecting into the yz plane, or x and z so you're projecting into the xy plane. So if you had that, then this part would be right, but you wouldn't have this down here. You'd have, depending on which plane you went into, you'd have two of the partials and then the other component. So the more general case for the flux integral would look like this, where you have the dot product with this cross product over the magnitude of it. This gets you the unit normal, and then you're going to have some kind of scale factor that depends on where you're going. So as integrals using the parameterization of the surface, the flux integrals are surface integrals, but surface integrals are not necessarily flux integrals, because the flux integral is this special kind where you have the dot product of a field and the unit outward normal as your function that you're integrating over the surface. And just the integral over the surface of some function or other doesn't mean that function is necessarily a dot product like this. So the surface integral is a more general situation, and the flux integrals are a subset of them, but they turn out to be important in applications, say, in physics and other electrical engineering and so on. So surface integrals can be one of several forms. What the book calls parametric in section 16.6. So you have the integral of some function of the three variables, and this sigma then would be parameterized, a surface parameterized with x, y, and z as functions of the two variables you're going to use as your parameters. And those two variables could be x and y, but they also could be the angles if you're on a spherical surface that you use in spherical coordinates, and they could be the r, they could be two of the cylindrical coordinates. If you're on a cylindrical surface, then that's r equals constant, and so your parameters would be the angle and the z. So then when you do the parameterization, you have your function of x, y, and z replaced however they should be with your parameterization, and then you put in this Jacobian, as we call it, which is your scale factor, and then the du dv. And this thing is not, in general, a flux integral because your g is not necessarily the dot product of any field with an outside normal. Or if it is, you don't necessarily know what it is. And so then if your surface is defined implicitly by some function of three variables equal a constant like this. See, this is your equation for a sphere, radius 3, center at the origin. So that you would say is defined implicitly rather than by saying it's the tip of an R vector with the radius of the sphere fixed at 3 and then functions of the two angles. So something like this then would be your function of x, y, and z, and then you'd take the gradient of that, and divide by the gradient dotted with a unit upward pointing normal. So you can do things that way. And then finally, the third possibility is your surface is defined explicitly like this, like on test 3, the top half of the sphere, and then your surface integral would be your function, whatever you might have. You see, this could be some kind of mass density function or charge density or something like that you're going to integrate on this surface. So whatever function it is you're given in the problem to be integrating, you'd replace the z with the formula for z when you're on that surface, and then your Jacobian is going to be this magnitude of the gradient of z minus f of xy, and then you dot that with k, and that will give you just the 1 as your denominator. So let's look at some examples of this. In problem 1 in section 16.6, we're given the function g of x, y, z is x. So that's like a density function, mass density, charge density, something like that. And we're given our surface parameterized like this, x, x squared, and z. So you see what we have is essentially y equals x squared. And you see here's a picture of our surface, y equals x squared. As you know, in a plane, it would be a parabola, and then if it's 3 dimensions, you have the parabolic cylinder, as it's called. So we're told in the problem that x runs 0 to 2 and z runs 0 to 3. So we do our partial with x, and you see we get 1 and 2x and 0. And we do our partial with z, and we get 0, 0, 1. And then we do our cross product, and we get 2x minus 1 and 0. I actually have that cross product here. If you set the thing up, you get 2xi, 0j, 0k, and coming back you have 0i, 1j, and 0k. So you get 2xi minus j out of it. Turns out problem 1 and the problem that's over there under the clock, it's a different problem, but they have the same surface. And so we do our cross product, and then our coordinate scale factor, or Jacobian, is the magnitude of this cross product, which if you dot it with itself, you get 4x squared plus 1 and square root that. So then your surface integral, notice it's not a flux integral. You don't have the dot product of the field with an outward normal to get your function that you're integrating. This is just a function that could be interpreted, as I've been saying this morning, as some kind of density, but it isn't necessarily something you can interpret as the dot product of an electric field with the normal. So your function, anyway, in this problem is x, because the problem says so, and you have your magnitude then of your cross product, your scale factor, and then you can integrate with the variables that are your parameters. So y and z, or x and z rather, that's an x. It's an x that kind of got smeared. So you would integrate this the way you'd expect to. This is a u substitution. If u were 4x squared plus 1, the du would be 8x dx. So you have u to the half, and then you have du over 8, and you change your limits to limits on u, and grind through that, and you get the number. So another way you could look at the same problem then is that your projection factor, which is this thing, is the magnitude of this, which we have here. And then what you're doing is you're integrating your projection factor times your x, which I should have written there, in the xc plane. That's another way to say what we did. I forgot to write the function. Take a look at some maple that I will give you. Vector calculus with problem 1. So you bring up with vector calculus, and then it'll do surface integrals if it's a standard kind of figure. You can type surface int, and then whatever the function is. See, that's the x. That's x because in this problem, our function of x, y, z is x. So that's this x. So it's this one. And then the vector calculus always demands that you say what your coordinates are. So you got the x, y, z, and then surface, and then you see you give your parameterization unless it's a standard sort of surface. If it's a sphere or something like that, you can say that, which you'll see as we work through some more of these notes. So with this one, your surface is defined in the problem as what's traced out by the tip of the vector x, x squared and z. In other words, y equals x squared. So it's the blue picture. And then you have to give your limits on x and on z, since those are the parameters as given in the problem. And back comes the answer. The only thing is, of course, it doesn't tell you at all what it did. So if you want to go through it, say R, give your parameterization. Capital R is x, x squared z, okay? Then what I'm calling A and B are those partial derivatives. So the colon equal is a defining statement. So A is the name I'm giving to the partial of R with x. And if you type this map and DIFF, DIFF is derivative, differentiate, and the map puts it in the form that you see with number 2, well, number 3, say, it puts it in component form, where the E sub x is like I, E sub y would be like J, E sub z would be K. And then partial with z the same way. Then you do your cross product, because that's what you do if you were doing it by hand. And that gives you line 5. And you see what it is 2x minus 1, where instead of the angle brackets and the commas, it's 2xi minus 1j, like engineers do with the ijk. Okay. And then the norm is the magnitude of the vector. And you see that's the same as what I have on the board. And then you can do double int, and there's my x square root. Same, line 7 there is the same as what's on the board. And then the value is the same as line 1. So you can follow it through this way, and you could use Maple to do all that if you had some reason that you wanted to. So notice that, as I'm saying there, the norm is the norm of the cross product, gives the projection factor, and that line 1 equals line 8. So let's go to problem 4, and you see that our function is z squared, because it says so in the problem, and our surface is the sphere with z greater than or equal to 0, so it's the top half. So if you do your parameterization, since you're on the surface where the radius is a, the natural thing is to go to the spherical coordinates, and so you're going to have the radius times the sine of the colatitude, the phi, times the cosine. In other words, r, it's like x equals r cosine theta, where small letter r is the radius from the z-axis over to your little box, and that's the a sine phi. It's the second here. Then what I have is the spherical coordinates for x, spherical coordinates for y, spherical coordinates for z. And so then if you take the partial of this with respect to phi, and the partial of this with respect to theta, which I didn't write down because I didn't have the space, and then do their cross products, you get this. Okay, and then if you take the magnitude of this thing, you'll find that you get a squared sine phi, which is your Jacobian for Cartesian to spherical. This is the same thing that we were talking about yesterday. If you think of the handout that you got yesterday that had, and I guess there are a couple people here that didn't get that one. This is the one that we reviewed yesterday that we talked about back in chapter 15. The Jacobian is also what we call the volume of this little box. I guess that's right, you weren't here either. We were talking about this yesterday, and the volume of the box in spherical coordinates is what you're really getting when you do the Jacobian, but you can produce it either as we did in chapter 15 by making a drawing and treating it as if it was a box, or you can actually do these partial derivatives and cross them, and then you can see that the magnitude of this will be here. You can see that a square comes out as a factor, and then you're going, when you dot this with itself, you're going to have the sine square as a factor, and then you'll have sine square theta plus cosine square, which is 1, and it'll work out. So your parameterized function, z square, then, is going to be, is going to use a cosine phi for z. So z is square. So then your z square is a cosine phi, the quantity square. So here's your z square, and then your magnitude of your cross product is here, and then you integrate with d phi and theta. So you do this integral, and you get 2/3 pi 4th, which is what book says that it is. Let's see, I don't know if I did that one with the maple or not. Let's see, I have problem 2 there. I have 3. I guess I didn't do that one with the maple, but anyway, you can see that how that works out. Let's look at some pictures here. One's enough. You have a picture that's more or less this picture, and then let's see, then I've drawn 2 and 3, and then again I didn't draw 4, I guess, either. So then let's go down to this end. if you look at problem 19, it wants the outward, and it says in the book, away from the x-axis, flux across the surface sigma, which is the surface that looks like this. Now, remember those first two integrals that we did in the other end of the room were not flux integrals. They were just a integration of a function that could be interpreted as a charge density or a mass density or something like that. Now these want the flux, so you're going to be given a field. So you know whether or not it's a flux integral by whether or not you're given specifically a vector field. If you are, then you have to get an expression for the outward pointing normal, and then unit normal, and then do the dot product, f dot n, and that gets you a function like the scalar function in problem 1 or problem 4, and then you go on from there as a surface integral. So in this one, this is the field, and I'm making this a parameterized function by using the equation of the surface, which is given as z equals 4 minus y squared. You see, if you're in the y-z plane, z equal 4 minus y squared would be this parabola. This is a portion of it, and it goes up to a high point when y is 0 on the z-axis at 4, and then it would drop down on the left-hand side over here where my left hand is. And coming this way, the lines that are parallel to the x-axis would all be level, like level curves as contours. And this would be at the crest of the roof, say, up here where z is 4. These would have fixed values for z from 4 back down to z equals 0, which would be here. So the parameters are x and y running 0 to 1 and minus 2 to 2 because the story says so. And so parameterized then, I've replaced the z squared by 4 minus y squared, x is x, and minus 3 is minus 3, and then z is 4 minus y squared. So this is the field parameterized with parameters then x and y. And so the parameterized r then is x, y, and then z replaced. Take your partial with x, partial with y, and cross them, and you'll get this. And so then your integrand in your flux integral, your f dot n, will be the f, which is this down here, dot your partial, your cross product of the partials, which is this, over the magnitude, so that this is a unit normal. See, as I wrote it here, the unit vector n is in this same rose color as the parentheses. So that's what's n. And then you notice the denominator here is the same as this, the Jacobian. So when it's a flux integral, that denominator cancels the Jacobian. That'll always be true, and it leaves you the surface integral f dot this cross product to integrate like we did in the other end of the room. So the f then is here before you replace the z, and the cross product which is your numerator, is the 0, 2y, and 1, and then you have that. So then what I've done, you see I'll have z squared with 0, so it doesn't matter that I never actually rewrote the z square like this. Doesn't matter whether I do or don't because I'm multiplying by 0. Then I have 2xy, and then here I have to replace the z. I have minus 3z where I replace the z with the parameter I'm using. And so I have this integral, 2xy minus times minus is plus 3y squared minus 12, and I integrate that, and that's what the book says it is. And with unless you have a physical problem, the sign doesn't have any particular meaning. If you are talking about a specific physical problem that involves the flux of an electric field or something like that, then you would have an interpretation to put on when it's minus and when it's plus. But for us, it's really just a number. When we talk after the Thanksgiving vacation about what are called the Maxwell equations, where you're talking about the electric field and electromagnetic fields, then the sign would be something meaningful to us. It'll turn out that there are the 4 Maxwell equations, and 2 involve divergence and 2 involve curl, and the 2 that involve the curl involve working with flux integrals. That's what all this stuff is for, and we'll finally get there. Okay, meanwhile, let's see, did I do a picture of 19? I can't remember just what ones I drew or not. So we have 6, and yeah, we have a picture of 19 on the next to the last page of your maple drawings. And you see it's essentially my sketch. And then let's see in the other set of notes. What I may not have done. 12. I did, well, I did 22, which we'll get to in a second, but I guess that's all you get from the maple. Let's take a look at 20. So this is the same parabolic cylinder, the blue over there, in that picture of problem 1, but it's between different limits. And now what we're doing is a flux integral across that surface. So our vector field this time is 0x squared and minus xc, and again our parameterization for the surface is the same, y equals x squared, and then the parameters become x and z. But now we have these different limits. Something else I better do. That's just one sheet of paper. So, do your R sub x and R sub z as we did down there, and here's the same cross product, which is the 2xi minus j, and then the magnitude. So now with your flux integral, your F dot N will be the F, which is this field down here, dotted with the cross product, which is this vector right here. Then to have this be a unit normal, you're dividing by the magnitude of the cross product, which also is the projection factor, or Jacobian, so again they cancel. And what it leaves you for what becomes your scalar function to work with in a flux integral is this dot product, which is here, and then you integrate with whatever are the parameters. And so you have 0 times 2x, and you have minus x squared, and 0 times minus xz, so it's the surface integral then of minus x squared dx dz when all is said and done. And so you'd integrate this without any great trouble into minus x cubed over 3 and put in your limits. And then that number, which proves to be this is a 2/3 here, and then the minus, so you have minus 2/3, and then you integrate z 0 to 2, and that gives you minus 4/3. So let's finish here with problem 22, which is a rather interesting problem because it relates to what we'll be doing a week from today, which is called the divergence theorem. So first of all, take a look at the maple. And I believe that, let's see, I drew 19 and 20. I guess I didn't draw 22, but I think if you look at the other part of the maple where I'm actually working with the vector calculus package, you see it's on the front side of the last sheet of paper. And it says problem 22. So you can type flux vector field, and again, what the field is, and then Cartesian, and then if your surface is a standard sort of surface, like a sphere, you can type sphere, and you have to type what the center is. So center at the origin, and what the radius is. And you see it just gives you the answer for pi cubed. You can also do flux vector field, Cartesian, sphere, and you type inert so that for line 37, instead of giving you the answer, it will give you the setup of the thing. So the setup, the a cubed sign that we have there, is what I have on the board. Another way you could do this, if you type your R, so this would be the line 59, so that's your parameterization on the sphere. That's essentially like my handwork. Then the the partial derivatives, the A is going to be, I'm using P for the angle phi, the Greek letter phi, and I'm using T for theta. So partial derivative with respect to phi then is line 60, and partial derivative with respect to theta is line 61, and then I do the cross product, line 62, and then I parameterize the vector function that is the field in my flux integral, so that's the F. Line 63 is the x, y, z, which is your field parameterized with the spherical coordinates. And then I do the dot product, that's the line 64, and simplify. And you see I get, in this case, the same thing as what has been the Jacobian. The reason for that is my field in this problem, x, y, z, is the same thing as my r vector, if you wrote it in Cartesian coordinates. And then if you integrate, as in line 66, you get the answer that we see that it is the 4 pi a square. So let's look at what I just ran through with the maple here by hand. So for this field, which you notice is the same thing as what would be a position vector, x, y, z, it wants the outward flux across the sphere centered at the origin. So our parameterization on the sphere then, this is x, this is y, this is z. So I'm using the spherical coordinates, but it's a Cartesian form vector. And we know from working with this enough, certainly, that if you take the partial with phi and the partial with theta and cross them, that you end up, when you do the magnitude of that cross product, with this. This is the volume of the box, if you want to look at it that way, that goes with spherical coordinates, and it's the projection factor, or Jacobian. And the ds then, for working on the surface with the two spherical coordinates as your parameters, is d phi d theta. So the cross product then of these partial derivatives gives you your outward normal, which works out to be this. And the parameterized f is the same as in this problem as the r, because of what f happens to be. That's a happens so, but we can use it. So our f dot n, then to make the unit vector, you divide by this Jacobian, and then you multiply by it to allow for your scale change, to let you use the new coordinates. And so that gives you your f dot unit outward normal. So you put in the f, and the so what you get looks like this, and then you factor the sine cubed here, and you have cosine square plus sine square, which is 1. So now you have sine cubed and sine, so you can factor out a sine, and then you have sine square here and cosine square, and that's 1. So it collapses down like this. So your f dot n becomes a cubed, sine cubed here, sine phi, cosine square, and then as I said, you write this as sine times sine square and factor out the sine. And so finally, this is what you have left to integrate, and when you integrate that, you get 4 pi a cubed. Now, the interesting thing is how this relates to what we'll do next Friday, called the divergence theorem, which says that the flux integral over a closed surface like this, a sphere, is equal to the triple integral of the divergence of the field throughout the volume that your surface encloses. And so if you do the divergence of this field, you see you have del dot your field here. So you have partial of x with x, that's 1. Partial of y with y, that's 1. Partial of z with z, that's 1. So your divergence is actually 3. So when you do the integral of 3 over the volume of a sphere, you get 3 times the volume. Well, you know the volume of a sphere is 4/3 pi a cubed, so 3 times it gives you this, which is what your flux integral gives you. So the last theorem in the book, really, in 16.8 next week, is what I've demonstrated there, that you do a flux integral over the outside of a closed volume. It has to be a volume that would hold water, like a sphere. And you're talking about an outward pointing normal that you would have to represent, as we have in this case, as this cross product of these partial derivatives. Well, over here, I was pointing at the wrong problem. You integrate that over the surface as your flux integral, and what you get will equal the triple integral throughout the volume that this surface enclosed of the divergence of whatever the field was. Gauss originally proved this, and it's important in getting at how you relate these things to electricity, which we'll see the week after vacation. So, anyway, you need to get some practice doing these flux integrals on surfaces, so I guess I'll let you go do it. So I'll see you Thursday if all goes well.